I want to do this time is show you a illustration of an MLE for a continuous distribution. Guys, I promise you I can spell. I just can't write. And what we'll do is we'll take a look at this with the normal distribution. But guys, let's review the steps. I never know if, when you guys are going to watch these videos, whether you're going to watch them back to back, or there could potentially be a couple of days before between watching video. Heck, there may be a couple of days between stopping a video midstream and watching the rest of it a few days later. So anyway, finding MLEs, the first thing we need to do is usually know either the density or the mass function. Can't proceed without that. The second thing we need to do is we need to think about the random sampling and create our likelihood function. The third thing we need to do is we need to take the natural log of the likelihood function. Ultimately, we're going to take the derivative of the natural log of the likelihood function with respect to the parameter space and set it equal to 0 and solve for theta. Now guys, keep in mind theta, we've looked at situations where there's been one parameter, getting ready to look at one where there's two, but we're going to look at it in a special case. The fourth thing we need to do is take a look at the second derivative, so verify using the second derivative that we have a min or a max, and guys, usually maximum likelihood estimation. We're wanting to find a max. We're actually going to see that that's a little different here in this problem. Now, one thing to say about MLEs, it's kind of cool, and I would say it's an advantage of MLEs, is that any function of an MLE is an MLE. Seems rather harmless. We're not going to prove it. But what this tells us is if we can come up with the MLE for, say, the variance. So our MLE would be the estimate of the variance. Then we can take the square root, which would be the function of. So square root of the variance is clearly the standard deviation. And this is also an MLE. All right, so pretty cool. That will become an issue soon enough. So for some reason I'm freaking out. I feel like I'm not recording. Actually, I am recording. Cool. All right, guys. What I want to do now is switch gears completely, and well, completely. We're still going to be doing MLEs, but I want to take a look at a little more difficult problem. I don't know. So let's say that our function, our goal is to estimate mu. And we're going to use maximum likelihood estimation. And so we're going to collect some data. And x1, x2, up to xn. And let's say that this is a normally distributed random variable. All right, get the gist. All right, so again, we want to estimate the parameter, which in this case, our parameter, if using notation from previously, would be mu. So now, as we talked about earlier, first thing we've got to do, go all the way back. Very first step is we've got to find our density mass function. In this case, it's our density function because we have a continuous distribution. So the function that we're going to use in this case is, I am sure you know, everybody's favorite, is probability in this density function for a normal distribution. So ultimately, guys, our goal is we want to maximize product from I equal 1 to n. Again, where does this I equal 1 to n come from? It comes from our data. We have 10 measurements here. So we want to maximize the product of 1 over and I'm going to rewrite this a little bit. Is this. You guys, every bit of that is in the exponent. So, guys, again, we've got these observations. Our first observation, next observation, our n observations. So we're going to have this set up as 1 over sigma square root of 2 pi e negative x sub 1 minus mu squared over 2 sigma squared times 1 over sigma square root of 2 pi e negative x sub 2 minus mu squared over 2 sigma squared times dot 1 over sigma square root 2 pi e minus x sub n minus mu squared over 2 sigma squared. And guys, obviously that can be written in using the product shortcut notation. Okay, so let's try to make this look a little bit better. Right? First of all, if we're multiplying all these things together, you can see very, very, very easily that you can bring one standard deviation to pi raised to the nth power. You can bring that out front because every single term we had one of these. And if we have this one times this one times this one n times, it's clear that we have n of these. What's up?
Nothing.
Okay, let me finish this lecture and we'll be okay. Now, go back to the next page, and we've got to take care of these. Well, e to those. So again, we have a common base e, and we all know that we add the exponents when we multiply common bases. So it should be no stretch of the imagination that we're going to have base e, and we're going to have negative x1 minus mu squared minus xn minus mu squared, all divided by 2 sigma squared. Guys, I've run out of space here. There we go. Now, this part right here is a constant. And when I'm trying to find a maximum value of something, you have to buy into the fact that the constant, it's not a function of our parameter mu. So this is just going to be a value, because we're assuming, I don't know if I mentioned this, and I should have, that we're dealing with a distribution where the variance is known. So this is just going to be a value. So this is going to be a number. There we go again. So if I'm trying to find a maximum value, for example, of 5 times any function, if I can maximize this value, find the value for which this value is maximized, clearly the 5 is not a critical player in that. All right, guys, let's examine this part right here. All right, let's examine this part here. So we're taking this out of the equation. So I got to stop my equal sign. But what we want to do now is we want to maximize e to the we want to maximize this. And again, we do have this but when we're dealing in a situation in this one where the variance is given, this again is going to be a constant. Now, from the previous page, I haven't done anything fancy at all. Just cleaned this up and factored out the 1 over 2 sigma squared, factored it out. Okay, now when I have, for example, if we examine this part right here, I can actually find a maximum value here if, because our exponent is negative, if I actually minimize the exponent. Now, I'm not sure if that makes sense or not. Okay, let's let's look at it this way. If I have something like I don't know, 5 to the negative x squared. Well, guys, this is clearly 1 over 5 to the x squared. And if I can minimize this value, I make this the minimum value, which will create my fraction to be the largest value. So that's kind of what I'm doing here. So I want to find a value for which yeah, let me go back here. So we want negative. So we want to find the minimum value of this. Now, from the same argument before, if this is a constant, I can find a minimum value here when this value is a constant. I'm sorry, this value is the minimum. Because again, we're working on the assumption here that the variance is known. So we're trying to estimate mu. Okay, so what we end up getting is something pretty straightforward, right? So this. Now what I'd like to do is expand each one of these. I'm going to test your foiling. Of course, we all know that this is the case, right? Sorry, couldn't help myself. All right, so we call it the freshman mistake, right? All right, so we're going to have here, we're going to have x2 squared minus 2x2 mu plus mu squared plus dot 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 x of n squared minus 2 x of n mu plus mu squared. All right, guys. Now, we can start grouping things, and the first thing I see from this, I'm going to have to go back and forth, is I'm going to have, when I add all these up I'm going to have this when I sum up my mu squared terms. The next thing I see that I'm going to get is my first terms And this is what I'll end up when I sum my x sub I squared terms. And then the other terms that I get, I forget, so we've got the negative 2x1 so I'm going to have, okay, so negative 2 x1 mu, negative 2 x2 mu, negative 2 xn mu. So I can clearly factor out a negative 2m, negative 2 mu out of these. And just get x1 plus x2 plus xn. Okay, and guys, this clearly can be written as negative 2 mu sum I equal 1 to n x sub I. Hold on, what?
We're going to be at the Martinez's.
Okay, I'll be done in about 15 minutes. Okay, now, if we put all this together, we're going to end up with something actually pretty darn cool. So we have n mu squared minus 2. Let's write it x sub 1 plus x sub 2 out to x sub n mu plus the sum I equal 1 to n of x sub I squared. So guys, clearly we have, I want to get the consistent notation through. All right, guys. So let me step back from this and make sure that we've got what I want. But it doesn't matter what I want, it's that I've got what I'm supposed to have. All right, now what I want you to think about is, I want you to think about this as a quadratic. And I want you to think about this as ax squared plus bx plus c. So guys, obviously our a term is n. Our b term is 2 some xi's. And our c term is the sum of our x sub I squared. And obviously our x is our mu. Now, also notice that our leading coefficient n here has to be bigger than 0. We're going to look pretty goofy if we start collecting negative sample sizes. So this tells us that we're going to have a parabola somewhere that opens up and very, very nicely that our vertex is our minimum. All right, guys, how do we find a vertex? Let's review a little bit about completing the square. Uh, if I can even remember how to do this. Uh, all right, if we have ax squared plus bx plus c equals 0. If we factor out an a, we'll get x squared plus bax plus c over a equals 0. And what we can see, to complete the square, what we ultimately need to end up with, obviously, is x plus something, and then, our stuff we'll take care of out here in just a second. Well, what we know that we put there is we take our b term, divide by 2, and we square it. So it looks like we're going to have b over 2a quantity squared. So guys, we're going to, it's been 100 years since I've taught the completing the square. Well, not 100, but. All right, so guys, right here we need to go x squared plus b over ax plus, so we're going to have what, b over 2a, so we're going to have b squared over 4a squared. But guys, we got to do algebra correctly, and if we add something, we can't just change our quality. I tell my students all the time, if we can just go in and change things arbitrarily, I'm going to go to my bank and add a couple of zeros to my bank account. Guys can't do that. If we add something, we have to subtract it when we're dealing with inequality, because we can't change the value of the problem that we start with. Well, guys, anyway, we're gonna see here that we have x plus b over 2a quantity squared. And let's see, out here we're going to get, I'm going to come in and change a little bit. Can I go in and change some? Yeah, let's go in and change a color here. All right, so I want to make this 4a squared. So I've got to multiply by 4a. All right, so I'm going to get negative b squared plus 4ac all over 4a squared equals 0. Now we know that the vertex, when we get in this form right here, we know that the vertex of our polynomial is going to be in the form and I'm just going to put stuff. So we know this right here is going to be the x-coordinate of our vertex, which by the way, very nicely creates the minimum value of the e to the power, which ultimately creates our maximum value. So I need to look at this negative b over 2a And now, so remember, guys, we've got I'm losing my place here. We've got n mu squared minus 2 mu. Okay. So we've got n mu squared minus 2 mu sum from I equal 1 to n x sub i's plus sum from I equal 1 to n. And I'm sure you see where this is all headed. All right. So our negative b, again, this is ax squared plus bx plus c. So our negative b would be, and again, you got to think about this mu. This is equivalent to our x. So our negative b up here would be negative 2 I equal 1 to n x sub I over the quantity 2 times a, which is n. So a little trickery here. Negative negative gives us a positive. Come in and start whacking some stuff. Our 2's cancel out. So guys, what we end up getting is the sum from I equal 1 to n x sub I over n. And there should be no mystery here. This is nothing more than our sample mean. So what we found is from our observed data, that comes from a normal distribution with unknown mean, known variance, that the MLE of mu is x bar. Exactly what we thought it